Hello, my name is Sinwoo Kim, and this is my fourth lab report for Physics 2211. This report will consist of the introduction, fundamental principles, experiment, computational model and code, results and discussion, and finally a conclusion. The purpose of this lab is first to observe the motion of a spring mass system where the mass is swinging in an arc while it oscillates on a spring. This will give us the observed position data. Second, we will calculate expected position data from a computational model of our experiment on GlowScript using Newton's second law. We will compare the two position data and use the energy principle to calculate changes in energy throughout our model. To summarize the results, our observed versus expected x and y position data match well, but the y position shows some deviation. Also, our system's total change in energy remains zero, demonstrating that the energy principle is satisfied. Now we will talk about Newton's second law. It states that the acceleration of an object depends on two factors, net force and mass of the system. F net equals mass times acceleration. By manipulating this equation, we can derive two other important equations used in this lab, the velocity update formula and the position update formula. These will be used to calculate expected position data. A new fundamental principle being used in this lab is the energy principle, also known as the first law of thermodynamics. It states that total change in energy is equal to work done by their surroundings plus Q, the heat added to the system. Q is equal to 0 since we're only looking at conservative forces. The experiment was recorded on video and provided to us. A mass was swung in an arc while oscillating on a spring fixed at the top. The system is the mass, spring, and earth, and the surroundings include nothing. Now looking back at the energy principle, there are no surroundings to do work, so keep in mind that in our experiment, delta E is just equal to 0. I then tracked the position of the mass over time using Tracker. The experiment was uploaded and calibrated to scale. The origin is set to the fixed point of the spring, and the mass's initial position was found. The mass is 0.402 kilograms. The spring stiffness is 6.83 newtons per meter. The time starts at 0 seconds when the mass was swung. Each time step between tracker points is 0.095 seconds. We are focusing on these data points that Tracker gives to us, which will allow us to observe x and y positions of our mass. To create the computational model, I first had to set the initial properties of the experiment taken from Tracker, which are the ball's mass, position, and initial velocity that I found using the change in position divided by the change in time between the first 2 points in the data. Additionally, I also defined the important constants, which are the gravitational constant near Earth's surface, spring constant, and the relaxed length of the spring, which was measured to be 0.123 meters. Then I added code to specify the vector L of the spring, the unit vector of L, and the stretch/squish of the spring. Lastly, I calculated the initial energies present in the system and added them together to get the total energy. The three energies present are kinetic energy of the mass, gravitational potential energy from the Earth, and spring potential energy from the spring. Our assumption here is that there is no air resistance acting on our mass during this experiment. Moving on to the calculation loop, for each consecutive time step we need to use Newton's second law to update the mass's velocity and position. For this, we need the current net force, which consists of gravity and the spring force. We can plug this into the velocity update and position update formulas for each time step to obtain the expected position data. Lastly, the spring's details are updated and the total energy is calculated again to find the total change in energy compared to the previous initial energy at each time step. This is an image of our model after it has finished running. The red is our real-life mass compared to the blue mass from the model and its blue trajectory. Here are the observed and expected position data plotted on the same graph for x and y separately. The observed x positions fit the expectations very well, whereas the y positions deviate a bit more. Therefore, we need to cover possible sources of error. The main source comes from manually having to track the mass's position on Tracker, which can be quite difficult since it's an object on video being clicked on by a mouse cursor. It can be hard to tell if the mouse is clicking precisely on the center of the mass. Also, the lower quality of the video causes motion blur and makes images unclear. Another source of error would be that in reality, air resistance likely exerts some force on the mass, though our models assume that there is no drag. Lastly, it is not likely for our system to be truly isolated from all surroundings. The work done by the surroundings may not equal 0. To conclude this experiment, here are some questions pertaining to our models. What does it mean? Is the energy principle satisfied? Discuss the energy change plots. Yes. In our model, the total change in energy, the orange line, remains 0 because there are no surroundings or external forces acting on our system. This satisfies the energy principle, which states that energy cannot be created or destroyed, but rather it is transformed between the different types of energy, as you can see with the red, blue, and green lines. Estimate the period of oscillation using the x position data and then the y position data. Compare. I estimated the period of oscillation by finding the same peak or crest twice along a data column, x or y, and then finding the amount of time in between, aka one oscillation. Using the x position, the estimate is 1.71 seconds, and using the y position, the estimate is 1.52 seconds. The period was shorter when estimated using the y position data, but both estimates are still relatively close to each other.